where we know that there's multiple degrees of freedom and their energy scales are similar. And when they start interacting in the same systems, then we can see an emergence of exotic phases like superconductivity, magnetism, so on and so forth. Um, and in parallel is the bottom thrust, where we have learned to recognize quantum materials by a new classification scheme, which is topology. And this is for a long time progressed along the line where single particle description of our systems was quite proficient at identifying novel topological phases. And then I think increasingly in the past few years, the field has really started to recognize that it's very important to look at systems where where we can have both correlations and also topology. So, so therefore, this motivates us to study in systems that host these topological quasi-flat bands. So before I get there, I want to introduce our primary tool, which is angle result photon emission spectroscopy, or ARPES. And just for the younger audience amongst us, I thought I would throw in this slide to introduce the technique. This is the photon in, electron out technique. Essentially, we can shine photons on our samples, sending in vacuum, and then the electrons will be ejected because of the photoelectric effect, and then these photoelectrons are then captured by this electron analyzer, which then measures the momentum and energy of these photoelectrons. And because in this photon emission process, the energy and the momentum are both conserved, therefore we can actually back out this energy versus momentum relationship of the states from which these photoelectrons were emitted. And therefore, this is a direct way to measure electronic structures of quantum materials. So typically, the data that I will be showing you are taken in the form of these two-dimensional cuts. And these are having axes of energy versus momentum, and you can recognize it's a parabolic band. And then we can only measure states which that are filled. Therefore, we can only measure states that are below the Fermi level. And of course, you can imagine if you take a bunch of these parallel cuts in momentum space. I'm sorry, just use this. And therefore generate these entire cubes of electronic states. And from this, you can generate any kinds of cuts that you wish. And the other popular type of measurement is these so-called constant energy contour cuts. And if you measure these at the Fermi level, then this is direct measurement of the Fermi surface. So please feel free to interrupt any moment if you have questions. Okay, so I want to also say a few words about what we actually measure from photon emission. A lot of times people think of ARPES as a tool just to map the electronic structure. But really, what we measure with photon emission is a single particle spectral function, this A of k of omega, which contains both the band dispersions, which are these energy as a function of momentum k, but more importantly, we can also capture interaction effects, many-body effects through this self-energy term. So in the self-energy term, we can essentially look at the way that the electrons are, the way they live in these various different types of quantum materials. So I just thought I would show you some examples of how we actually look at correlation effects from ARPES data. So if you think in the limit of non-interacting electron systems, each electronic state are these delta functions. So what that means is that they have zero width, which means they have infinite lifetime. So therefore, this is really the most coherent limit. You have these dispersions with full spectral coherence. If you start input correlations, then you can see that the spectral function gets split into a relatively sharp piece that looks like the non-interacting limit. And then also a term which is these broad humps, right? So in essence, we can describe this kind of system by looking at how closely they resemble the non-interacting limit. And so by looking at the quasi-particles, or these sharp peaks, there are various ways we can extract this quantitatively, this correlation effect, right? So one way that this is modified is that the overall spectral weight, or the area under the peak, sharp peak, gets reduced by this coherence factor Z, which can be a function of K. The other way that it modifies the spectral function is that you will see overall shrinking of the bands in energy, and this is known as a renormalization effect. And this is also another measure of how strongly correlated our systems are. So directly from photo emission measurements, we can have a way to look at these correlation effects. Of course, if you keep going in the limit of a Mott insulator, then your spectral weight under the quasi-particles are completely gone, and then you have an insulating state or Mott insulating state, right? So in a real system, such like as this iron-based superconductor, we can look at these, this RPX spectra, and then compare them to what's calculated from DFT. And in general, for many of these states, you can actually look at, there's a way to renormalize the bands of the LDA to get a reasonable agreement with the measurement. And that factor, the renormalization factor, is a gauge of the strength of the correlation effect, right? So this is a direct way to quantitatively extract these correlation effects from the single particle spectral function measured by RPS. Okay, so that's the intro. Coming back to the topic of flat bands, since I'm going to focus on flat bands, I just wanted to talk a little bit about why this is interesting. So we know that when you call a band to be flat, you must be comparing that to something else, right? You have to compare two energy scales. And in these systems, for a flat band, the important energy scales is, one is the Coulomb interaction U, and the other one is the bandwidth, which is the hopping of the electrons or the bandwidth. So then you can imagine the two limits in one situation, such as on the top, you can have, does this work? Maybe, sorry. So on the top, you can see the limit where if your Coulomb interaction is small compared to the bandwidth, bandwidth being essentially the energy range by which your bands are extended, or it's another way to measure this is by the slope, which is the velocity of the electrons. In that regime, we don't really need to include electron-electron interactions to get a decent description of our system. In the other limit is when your Coulomb interaction is much larger than your bandwidth, then you can see that this is where the particles become more localized in space and delocalized in momentum space. And in this regime, the interesting thing is that the entire bandwidth or states that are, that are in the momentum space can respond to interactions of that scatter via different wave vectors. Therefore, this is a regime where you expect to see more emergent phases arising in your system, right? So, therefore, this is why I think a lot of the community are really pushing to look for flat bands in quantum materials and try to tune them to the Fermi level to really look at whether these flat bands can induce interesting emergent phases. So since we have two parameters to tune, it is also fair to know that there are different ways to get at a flat band, relatively flat band. Here in this very nice paper, it's discussed the various types of flat bands, right? So one way to generate flat bands is by increasing the Coulomb interaction U. In that situation, this is like flat atomic bands. In that way, spatially, these wave functions are really localized on atomic sites. There's no overlap, or very little overlap between the wave functions. And here, this is really driven by strong Coulomb interactions. In the other limit, we can also imagine if you tune down W, or the bandwidth, to be small compared to the Coulomb interactions, then we also have another regime where, sorry, this point doesn't work really. You have the other regime where instead of having localized, spatially localized wave functions, these block wave functions are actually extended. But here, we can have a situation where the hopping is quenched. And this is actually the regime where I will spend the rest of my talk on and discussing the various ways we can induce this kind of topological flat bands by looking at lattices that have this kind of destructive interference effect on the electron wave functions. Okay, so before I actually show you our data, I want to take a minute to just show you some examples that has been extensively studied in the community in the two regimes, so that we can see like what to be expected on the two limits, right? So let me first give you some examples of the situation where we have atomically localized wave functions. Right? These have been studied for a long time, and a very good example is that of heavy fermion systems. So here, the F electrons are really localized on atomic sites, as represented by arrows here. And that's in momentum space are these flat bands. And then there's also conduction electrons, which are these squiggly lines. Those are usually orbitals of SPD electrons. And it has been demonstrated you can have two regimes. In one regime where there's no interaction or coupling between the localized moments and also the conduction electrons, then you don't actually observe the localized states. You just see the dispersive states. I'm sorry. I don't know if anybody has a laser pointer that, I don't know. I'm sorry that my laser pointer sort of ran out of power. But okay, sorry. Yeah, and in the other regime, you can have Kondo coupling between the two types of electrons, and therefore you can actually have a hybridization between the flat band and dispersive states. And this is the states you will see, and this is the two regimes one can reach with the sun under the. Thank you so much. I'm sorry. Thank you. Okay. Thank you very much. So this is one example. Perhaps I can show you another example which occurs in a milder fashion, and you can actually use photoemission to look at how it goes from one to the other. And that is something we studied some time ago in these iron to cautionite superconductors. So what I'm showing you here on top is ARPAS data taken on this iron, tellurium, selenium. And from left to right is the band dispersions around the gamma point shown when you vary the ratio of tellurium and the content of tellurium versus selenium. So here, what's under these dotted lines are the bands around the whole pocket. And as we know that the curvature of these bands is inversely proportional to the mass, you can visibly see that this blue one, this one which I labeled XY, is a band that has visibly flattened as you go from one end to the other. And also what this indicates is that the effective mass of that XY orbital becomes heavier and heavier as you go towards this end. So what we're really seeing here is that this correlation effect is orbital dependent. Because if you look at the other orbitals here, their bandwidth or their slope or their effective mass don't really change as you go from one to the other. A way to capture this is by this slave spin calculations by Timel's group and also together with Jensen's group. So here, what you see is that all this pink stuff here are the conduction, the itinerary electrons. And this one, that's really flat one, that is the XY band. So already in this regime, the XY band has a much lower coherence compared to the others, and also has a much smaller bandwidth, right? And then as you go from this regime to this regime, the XY band loses the coherence, the spectral weight disappears, and then in this end, this becomes completely not localized. And so therefore, the hybridization with the dispersive states gets turned off, so that in this regime, if you look at the Fermi surface, there's actually a reconstruction of the Fermi surface. This is the calculated Fermi surface, and which induces a new pocket around a zone boundary. And this is what we observe experimentally, the change from one to the other, which is consistent with this picture, that you have this correlation-driven flattening of the band. Okay, and then in addition, what we can also see is that as we traverse this tuning axis, or also in the temperature regime, we can see the spectral weight for this band disappears eventually. And that's shown here experimentally by these fitted points, which are the areas under the XY band as a function of temperature. Okay, so that is what we already know, and also similar to the cuprates and other systems for the regime where the flattening of the band is driven by correlation by Coulomb interactions. Interestingly, in the past couple of years, there's been a dramatic amount of activities on the right-hand side of the flat band, and that is the quenching of the kinetic energy produced by the special geometric frustration of lattices, Just to show you an example, the most well-known one is this one, which is a Kagome lattice. So Kagome lattice, the word Kagome comes from this basket weaving pattern seen a lot in all kinds of ancient history. And it's the lattice itself are these corner sharing triangles. And the interesting thing for these is that there is a destructive interference of the electronic wave function such that there's no hopping out of these hexagonal hexagons. So that these two are destructive interference such that there's no hopping out. So as a result, the band described by this has no bandwidth, and that's also known as the flat band. And except the difference is that in these flat bands, the wave functions are actually extended rather than localized on sites, but with the quenched bandwidth. And so this is what you actually see if you carry out tight binding calculation, only considering the nearest neighbor hopping. And so with the flat band, with the touching of these two dispersive states, right? And so in real materials, of course, this is a simplified scheme of what you would see for a Kagome system. In a real material, of course, yeah, you have the interaction with the other lattice sites, and then this is the maybe one of the best known Kagome system, Copo 10, where this is the DFT calculation for the bands that derives from this Kagome flat band, and then this is the photo emission data showing you, really good, reasonable match between the two. So this is the work by the MIT group here. So then you may ask, how do we find systems that have this kind of destructive interference-induced flat bands? Of course, Kagome is not the only one. And there's been multiple efforts trying to search through to try to find similar kinds of lattices that can give you this kind of destructive interference. And this is one example, and where they've gone through ICSC and identified the most commonly occurring lattice motifs that give you these flat bands. And these are the most common 5, right? With Kagome being the most common one, followed by paracore and so on and so forth. And you can see in these tight binding calculations, the band is extremely flat. And there is in all of these, yes?
Are the Vanier states still exponentially localized in this case?
I don't, so, yeah, this is the, this is the description of, I don't know for the other ones, but this is the.
So you're saying on the Kagome, in this Kagome flat band, Vanier states have power more?
Yes, I think so, unless the theorists can.
The thing is, when you have spin-order coupling, you cannot linearize because these are topological.
Yes, thank you. Okay. But in real bulk materials, of course, they don't look like tight binding calculations. This is another effort by this catalog of flat bands. And you can see that there are real materials where sublattices actually exhibit these kinds of frustrated lattices, and you can see evidence of these flat bands that derive from those this geometrically frustrated lattices. Right. So there's a vast material basis there to let us explore. So this is the outline. So I'm gonna try to do a pretty overall view of what kinds of lattice motifs we have explored in our group in the past couple of years, and I will just go through them in this 3 categories. So I will first tell you a little bit about our work studying the 2D Kagome systems, and specifically we want to look at what is the origin and mechanism, also CEW, charge density waves in some of these 2D Kagome systems, and then go from 2D to 3D and show you some of our recent work exploring the 3D analog of the Kagome system, which is a pyrocore lattice. And then if I have time in the last bit, I'll show you some of our work finding a destructive interference that seems to be able to be switched on and off in this van der Waals ferromagnet here in the last bit. So let me start with the Kagome system. So I talk a little bit about the flat band here, but let me just go back a little bit and show you what other interesting features there are in the electronic structure of a Kagome system. So this is a band dispersions calculated by tight binding along the high symmetry direction This is the Brownian zone, so from gamma to K to M back to gamma. And this is a 3D view of this electronic structure of the two momentum axes. So this is the projection of the Brownian zone here is about this size. Okay, so the first feature is the flat band. Of course, if you tune the chemical potential to be within the flat band, this gives large density states. And at least theoretically, right, this will lead to stoner type itinerant firing mechanism. If you have, right, theoretically, at least this is what you would get. So second, there is a pair of these saddle points. Saddle point being that the band dispersion is hole-like along one direction and the electron-like along the orthogonal direction. And then strictly in 2D, this will give rise to Van Hove singularity with a divergent density of states. And so for Kagome systems, the second part is Dirac point. Dirac point, if you lower your chemical potential to the Dirac point, you would get Dirac points at the K point in the Brownian zone. This is if you have spin orbit coupling, this will give rise to finite barrier curvature and also anomalous Hall. The third feature is this pair of Van Hove singularities. Of course, if you tune your chemical potential to be at the Van Hove singularity, this will give rise to this divergent density of states. And the interesting thing associated with these that's been known is that your Fermi surface at that chemical potential looks like this, which in this idealized picture is a hexagon. And when you have this kind of Fermi surface, then there are 3 pairs or parallel sheets of the Fermi surface that would be unstable against this nesting across this wave vector. And so theoretically, this would give rise to, for example, a charge density wave that is 2 by 2. So it flows from this side to this side. And there are 3 of these parallel sheets of Fermi surface in this regime. So perhaps associated with this kind of a connection or predictions of these 3 features, there has been a lot of effort exploring different kinds of Kagome systems in the past couple of years. And I sort of summarize them in this way based on the type of orders that's been discovered in these systems. And this includes superconductivity, charge density wave, and also mechanism. So if you look at these systems, under the systems that have a magnetic order, there are 2 families. One is the so-called 166 family, and they're either manganese-based or iron-based, and they tend to have very high ordering temperatures above room temperature in the range of 300, 400K. And then the other system is iron tin, iron germanium, so on and so forth, that also have magnetic order. And then on this side, you have systems that have been discovered to exhibit CEW orders. The most prominent one is this so-called AVS or 135 systems, vanadium-based Kagome systems discovered by Stephen Wilson's group. And there's been a lot of very interesting activities in that regime, and then followed by this vanadium-based 166 compound that has also the discovery of a charge order. And then I put here, this is the finding by my colleague Peng Dai's group of charged order within a magnetic order in iron germanium, and I believe he will actually talk about this himself soon enough in the school. But I will also tell you a little bit about our study of this using photon emission. Okay. So with this in mind, I want to first look at the simple example of systems that only exhibit magnetic order and discuss the question whether this flat band, when tuned in the Fermi level, can give you a stoner type ferromagnetic order, right? So to do this, we are looking at the simplest binary Kagome systems, iron tin and iron germanium, and you can have different kinds of stoichiometry, but I'm going to focus on the simplest one, which is the 1-1 system. And both iron tin and iron germanium belong to this structural family. They're isostructure, and they're both made of stacked iron Kagome layers. And they both have a magnetic order above room temperature, and the form of the magnetic order is that within the Kagome plane, they're both ferromagnetic, and then along the stacking direction, they're both antiferromagnetically aligned. So this is the A-type AFM order. The only difference is that the moments are in plane for iron tin and out of plane for iron germanium. Okay. Interestingly, so we're going to start with a simpler one, which is iron tin. So because iron tin only has one order, and that is this magnetic order. So iron tin, I reproduce it here, has a ordering temperature about 366 Kelvin. This is what's measured on the ball crystals. And this has been studied by various groups in the past in single crystal form. And you can see that in this work by the MIT group, they've already identified the key signatures of the Kagome electronic structure, including Dirac crossings, flat bands, and also, Dirac points and flat bands. But because of this extremely high ordering temperature, this makes the single crystal studies very difficult for ARPAs to actually look at the evolutionary electronic structure across that temperature, because the sample usually die in vacuum before you reach there. So ultimately, we want to understand, does the flat band play any role in inducing the magnetic order here? To answer this, my postdoc, Zheng Ren, joined us about a year and a half ago, and then he brought with him his expertise in building an MBE system. So he built next to our ARPAS chamber a MBE system where he successfully grown iron tin, Kagome iron tin, in thin films, and this is this you can see the ordering temperature is bulk-like, and also this is a read pattern, and also by this direct transfer from the MB system to the ARPAS system, we can directly measure the electronic structure without exposing this to air. So the really interesting or nice thing about this is that it turns out these thin films are very robust. They can live in vacuum for like a week, and you can still measure and everything is reproduced. And then we can actually, it's very robust also to thermal cycling. You can go across this TN and then come back down. And then to our delight, all of the features remain, which means that this is actually a really nice platform for actually answering the question, what happens across TN? So before I show you the data, I want to first talk about what we expect in terms of the origin, in terms of the how we understand magnetism, potentially what to expect, right? So we know that there are two extreme limits of how to understand magnetism. One is that the Stoner-like mechanism where you have the spin, the band splitting into spin majority, spin minority, spin majority, spin minority states, and this exchange splitting should close right across the ordering temperature. That's the Stoner-like behavior. On the other limit is the local moment picture, and here the local moments themselves don't disappear across the ordering temperature. They just lose their correlation, their long-range correlation. Therefore, from emission perspective, the exchange splitting actually should still persist across the ordering temperature, except that there's no longer long-range or correlation. So the spin polarization actually should disappear. That's the thing that disappears across the ordering temperature, right? So as you can see that we can very easily distinguish these two pictures if we are able to go across the ordering temperature to examine the evolution of the exchange splitting as a function of temperature. Okay, just to show you some reference, this is the measurement from literature on iron film, which perhaps many people consider to be itinerant. Actually, if you measure the exchange splitting from full emission on iron films, which are these blue dots, this is the ordering temperature. You can see that the exchange splitting actually only drops by about half, and it actually takes much more elevation in temperature to go away. Whereas they measured also the spin splitting, and that actually, the spin polarization actually drops at the ordering temperature. So you can see even in iron films, there is still contribution from both. The description should really be somewhere in between the itinerant and local moment picture. Okay, so now onto our own data. So why should we understand the system as a ferromagnet? The way we look at this is that, remember, every layer Kagome sheet is ferromagnetic. What that means is that within that sheet, we can consider the bands should split into the spin majority, spin minority bands as the moments order. And then it's just the character of the spin up versus spin down changes as you go across the layers, right? So with this in mind, we collaborate with Binghai Yan's group and also Hengxin Tan, who performed the DFT calculations for us on this system. And you can see this picture roughly in the DFT calculations. So here on the left-hand side is the calculated density of states. You see this large peak at the Fermi level. That corresponds to these topological flat bands associated with the iron Kagome layers here in the band structure for the non-magnetic state. And then when they calculate the electronic structure for the A-type AFM order, they can see this flat band peak becomes split into two. And then when they project into the spin majority, spin minority states, they can see that those peaks correspond to the Kagome flat bands, which are in this case are shifted down. This is shifted up across the ordering temperature. So in essence, this picture should largely be at least is captured by DFT. Okay, so what do we see? So when we measure the band dispersions along some high symmetry directions in the Brilliant zone, we can actually identify this peak here about like between 1 and 1.5 eV below the Fermi level, which corresponds to the spin majority flat band states. Furthermore, we can track these band dispersions as a function of temperature, and we find that there are regions in the momentum space where we can capture the bands whose behavior with temperature corresponds to that of the spin majority states. Which by that I mean like when you raise the temperature, they go up, right? They move up. Whereas there are other regions, these are the states that actually are compatible with expected behavior of the spin minority states, and then as a function of temperature, they come down. So in that way, we understand these are indeed the spin majority, spin minority states, and then we can look at, carefully as a function of temperature, how do they evolve? Well, you see here, they are evolving energy, but if I plot the total amount in energy that they have shifted, that's the green stuff here, compared to the exchange splitting for that band calculated by DFT. I hope you can see that the amount of shift that actually happens across the ordering temperature is a small fraction of the actual exchange splitting from DFT. So in essence, this suggests that for iron tin, the magnetism should be largely local in nature as opposed to the itinerant stoner picture, right? So here, oops, our observation is consistent with the picture on the right? So the thing that's very interesting that's pointed out to us from Timel's group by Lei Chen and also Fang Xie, who are both here, is that the flat band here is topological in origin, right? Which means you can't really write atomically localized states for these, like the local moments that we are used to dealing with. So here they have constructed what they call the compact molecular orbitals. In this way, they can actually generate an orthogonal basis that's also complete. And then with this description, then therefore we can think about the object that's carrying the local moment as perhaps coming from these compact molecular orbitals, which are not like localized, atomically localized states, but extended like this. Right, so that's the information we've gotten by studying iron tin in terms of what's driving the magnetism in these Kagome systems, even though their flat bands are at the Fermi level. Okay, moving on. So having understood that, we want to next walk over to the region where, besides the same magnetic order, we also are starting to see a charge density wave order, and that is seen in the iron germanium material. Okay. But before I get to iron germanium, I want to say a few words about, just to introduce charge density wave order and the Kagome systems. By flashing the results people have observed in these AVS or vanadium-based Kagome systems, which only has a charge density wave order. So as a flash in the beginning, we expect, at least in this idealized picture, if you tune the chemical potential to be at the Van Hove point, we expect this kind of Fermi surface, and this will give you a nesting that would correspond to this 2x2 in-plane charge order. And that's been observed in the AVS system, and this is the experimentally measured Fermi surface. There's some deviation, but you can largely see some agreement with this picture. And this is the charge order has also been observed by STM and many other kinds of probes. Okay, so what about the situation in iron germanium? Okay, so iron germanium has been around actually for quite some time. It's not a novel compound. What was known about it is that it exhibits the same kinds of A-type AFM order below around 400 Kelvin. And so here is work from Peng Cheng's group and also our joint student Qiao Kunteng. And when they did neutron scattering, they can certainly observe the additional magnetic Bragg peaks up here due to the out-of-plane ordering, right? But to their surprise, when they ramp across 100 Kelvin, they see that there's actually the appearance of all these additional superlattice peaks. And if you do neutron scattering, you know that by analyzing the intensity of these diffraction peaks as a function of Q, you can actually understand if these are actually coming from magnetic order or from charge order, in this or lattice or due to lattice, right? So from here, by looking at this, they can see that this is really due to lattices. These are not magnetic peaks, which they also later confirm with X-ray diffraction, right? So what they see here is that iron germanium within the magnetic order state actually go into this charge order state with the same in-plane ordering as the vanadium-based Kagome system. That's interesting. How do I understand this? So again, let me show you how we understand the magnetic order here. The story is essentially the same as iron tin, right? Because they're isostructure, they have the same magnetic structure. If you do the DFT calculation, the exact same thing is seen, which is that you can consider each layer as a ferromagnetic layer, and then they split into spin majority, spin minority states. Fine, great. The interesting thing for this one is that if you look at where the Van Hove singularities lie, when you have the situation where you have the flat band here, then your Van Hove points necessarily must be farther below the Fermi level, right? So the interesting thing here is that when we split into the spin majority, spin minority states, the Van Hove singularity from the spin minority states actually gets levitated towards the Fermi level, and that you can actually track here in the DFT calculations, right? So at least theoretically, this is a picture that one can see that is reminiscent of what happens to the vanadium-based on 135. So experimentally, what do we see? This is a project together with Xiaokun Teng and also Ji Sebo, who is our postdoc joined with Bob Bergeron's group at Berkeley. And they've done full emission on this material. And just to make a long story short, they indeed observe the Van Hove singularities here very close to the Fermi level. So this is a three-dimensional view of the electronic structure of energy versus momentum. You can see this is a direct crossing at the K point, and these bands rise up to the Fermi level into what looks like a Van Hove band. How do we know it's a Van Hove band? If you zoom in, we got to prove that it looks like a Pringle. So if you take a high symmetry cut, you follow the dispersions along the zone boundary, it looks like a whole band, and you can track where the band top is. And then if you you look at the cuts parallel to this green bar. If you walk away, you can also track the top of the Van Hove band. And you can see that in this direction, as we walk in the perpendicular direction, the band top of this whole band tracks out an electron band, right? So what that means is that this is indeed a saddle point that is consistent with expectation of a Van Hove band, right? So in that way, it's actually it's reminiscent of what happens in the 135 system with the charged water. We can do more. We can look at how these bands participate in the CW order. If we lower the temperature, we can with ARPAS you can look at the spectral function at different momenta, and if you track the band at the Van Hove point, we actually see that if you go below the CW order, we see there's a gap which develops on the Van Hove band. And this is not the case for the other bands that cross the Fermi level. And we can do a very careful temperature dependence, and you see that the spectral weight or the gap develops onsets roughly at the CW order. And this is actually consistent with what is observed in the STM measurement. This is the dip in the density of states by the STM at the Fermi level, right? So here we can see a spectroscopic evidence for the opening of a gap in the CW state. Okay, again, this is just so in that way, we can actually see here, this is compatible with the expected 2x2 folding between the Fermi surface. Okay, so summarize the first part. What have we done? We've looked into the Kagome lattice. First, we look at what is the origin of a magnetism in this iron tin. And from that, we actually arrive at this local moment picture from these compact molecular states. And then second, in the case of iron germanium, we see that the effect of the splitting actually is to bring the Van Hove points close to the Fermi level. That alone is likely not able to drive the CW by itself, but at least we see that in this situation, the Van Hope points are pushed to the Fermi level by the magnetic order, such to set the stage for the eventual emergence of the CW order. Okay, all right. So next, I want to go into the 3D version, which is the three-dimensional pyrocore lattice, and show you some of our results in explorations in that world. Okay, so pyrocore lattice from studies of quantum spin liquid candidates. Actually, it's a 3D version of a Kagome lattice. And so whereas the Kagome lattice are these corner-sharing triangles, the pyrocore lattice are these corner-sharing tetrahedra. And you can see that there are ways to cut through a pyrocore lattice like this along the 1-1 direction, such that you can actually reveal these Kagome planes like this, right? And the destructive interference is actually still there in this 3D version. The way you can see this is that if we calculate the 1-year amplitude on the 4 sites, the site which is not contained in the Kagome layer has 0 amplitude. Again, that means you cannot hop across the layers. And then here in the pyrocore lattice, you have a three-dimensional quenching of the kinetic energy. So this should give you 3-dimensional flat bands. And indeed, if you do the tight binding calculation, considering only the nearest neighbor hopping, you got 2 copies of the flat bands and then 2 dispersive states. So this is the basic tight binding calculation for a pyrocore lattice, which has been known in the field. So what else? So from this, we can also read off another couple interesting points. One is that there is a triple degeneracy point. There are 2 flat bands, the dispersive states that touch at the gamma point. And also along the XW direction of the Brillouin zone, there is a Dirac nodal line. This is the case without Spermberg coupling. If you input Spermberg coupling, a couple interesting things happen. One is that there's a gap that opens at the gamma point, and you can get a double degeneracy point depending on the sign of your Spermberg coupling. The other interesting thing is that this Spermberg coupling gaps out the nodal line along XW everywhere except strictly at the X point. If you look at the X point, the bands are still stuck together. This remains gapless in the presence of Spermberg coupling, and there's a reason for this. The reason is this so-called non-symmorphic symmetry. How do you see the non-symmorphic symmetry? The easiest way to draw this, I guess, is to picture, this is the pyrocore lattice. If you take the center of each tetrahedron, that gives you this diamond lattice, and it's actually been predicted, a decade ago, that a diamond lattice has the screw axis. So non-symmorphic symmetry means you have a combination of a translation and either a rotation or a glide mirror symmetry, right? So here, in the diamond lattice, as you can see, traced out by this green stuff, there's a screw axis, and there is a symmetry, there's an operation. There's a symmetry which across this 4-fold in-plane rotation plus this quarter translation along this axis, and it's because of this non-symmorphic symmetry. Any band crossing at the X point, the Brillouin zone, remains a gapless 3-dimensional Dirac point in this. So that translates to the pyrocore lattice as well. Okay, so to summarize, then there should be 2 key things we look for a pyrocore. One is that the flat bands now are flat in all 3 momentum directions, kx, ky, kz. The other one is that you should have a Dirac points at the X point of the Brillouin zone. So the physics related to the pyrocore lattice, I just want to, it's brought to us by our chairperson, Chen and Seti from Timel's group, who first taught us about the pyrocore lattice. We went to look for this kind of physics in 2 specific materials. The first one that we stumbled upon is this lavas phase compound, cerium ruthenium-2, and it has a crystal structure that looks like this. If you take off the cerium atoms and you're leaving only the ruthenium atoms, you will see this pyrocore lattice here, right? This is the corner-sharing pyrocore lattice. And so we wanted to see how the pyrocore system, the electronic structure, is preserved in this compound. So we did this following exercise. So this is calculations by Jonathan Dellinger. First, we got to start with the pyrocore lattice. So he calculated the density functional theory calculation for just the pyrocore sublattice. And these are the topological flat bands associated with the pyrocore lattice. And then the next step is to put in these pink atoms. In this case, he first put in the lanthanum. You can see that there's some slopes, the bandwidth which is gained by these states, and they're also pushed down. And then next step is to replace the lanthanum with cerium to input right. You see the additional carrier introduced in the substitution, and then eventually, if you incorporate spin coupling, we can see that we can recover these DFT calculations for the actual material, and we can track that these are the states, including this little portion, which are originating from the flat band associated with the pyrocore lattice. Okay, so experimentally, this is the work by my postdoc Jiang Huang here. He did ARPES on this cubic system, and what he finds is that actually you can see this portion of this flat band at the energy associated with the helium lamp, and we know that at this energy you cannot have any contribution cross section from the F electron. So this definitely comes from the ruthenium D states. That's the flat band, which is originated from the pyrocore lattice. And then secondly, we can also see that at the X point, there are these direct crossings, which is associated with the non-isomorphic symmetry in these compounds, right? So in this system, then we actually can identify the two key signatures in associated with the three-dimensional pyrocore lattice. So I just want to also point out, this is related to the work by Joszkowski's group, recently published in Nature, with the same isostructure compound, calcium nickel 2, right? So that's also discussed there. So in the previous example, it's great. We can see some evidence of the pyrocore physics, but you can see that the pyrocore stuff gets hybridized with the other stuff in the lattice. So we want to look for systems where we hope to have the features to be preserved, right? So for this, this is again found to us by Chenden here. He dug through literature and found the spinel compound, which is copper, vanadium 2, sulfur 4. And in this material, the vanadium is the one that exhibits this pyrocore lattice. And here you can see that what's interesting is that if you look at the structure here, the copper is surrounded by 4 sulfur, and this is both basically a fully filled structure. But for the vanadium, you can see the vanadium is surrounded by 8 sulfur, and this is the partially filled state. So it gives us hope that perhaps the vanadium states are actually what's at the Fermi level, and therefore relevant to low energy physics. So he convinced Bingao here from Pengcheng's group to grow these crystals, and then we again, so we are happily on our way to study this compound. So just to show that this is actually true, we carried out DFT calculations here, and you can see the extremely flat band here. Different from the case of cerium-2, these flat bands are actually quite flat, much less perturbed by the rest of the stuff. And this is coming from vanadium T2G states. And you can see that also in the density of states, this huge peak, which is sitting about half eV above the Fermi level due to the pyrocore vanadium sublattice. So Jiang again carried out ARPES on this, and to his surprise, you see this is the energy versus momentum states images. And you can see this extremely flat feature, which you can also see more convincingly from these energy distribution curves, which are essentially vertical cuts through this color image. And you can see this peak everywhere hugging the Fermi level, which suggests that this seems to be the pyrocore flat bands that we were looking for. But the question is, in the DFT calculation, that stuff is very far away from the Fermi level. It's half eV above, but experimentally we actually see them to be at the Fermi level. So why is that? In essence, make a long story short, this reminded us of what we observed previously for the iron tricogenide stuff, right? So you have multiple orbital system, and here it seems like perhaps you have certain stronger correlation associated with certain orbitals, and that is what could be the reason for bringing this down. So, again, working with Tim Yao's group, they have done a slave spin calculation for this compound, and what they see is that when they input Coulomb interactions, they can bring down the flat bands towards the Fermi level. And you can see even besides the flat band, even the dispersive states are now in much better agreement with what we observe from full emission compared to the onward normalized DFT calculations, right? So here, one step above what we found from serum CM2 is that there seems to be two effects at play. One is the destructive interference, which gives us the topological flat bands in the first place. And that's by quenching the kinetic energy. And then at the same time, there's also equilibrium interactions, which further normalize the states towards the Fermi level. And it's these two effects that are both in play that really amplify the correlation effect in this material, therefore producing this flat band that we see at the Fermi level. Right? So in that way, it's actually reminiscent of the situation in heavy fermions and also the iron-based superconductors with the superconductive correlations. Okay, so I'm coming to the end. I know I'm quite a bit over time. So I will, for that, I will just only show you two slides about what's interesting about the last example. Please bear with me. I think this is interesting. So this one we completely stumbled upon by accident, but it's actually, given what we have learned about the topological flat bands, this actually was quite fun to work with. And it turns out that in this system, which is the van der Waals ferromagnet, certain atomic sites have vacancies, and it turns out those vacancies can be ordered or disordered depending on how we thermally treat them. And the consequence is that if you look at the band, or if you look at the crystal structure, if you have vacancies that are completely disordered, on average, that you have, it preserves a honeycomb lattice. But in another stable state, the vacancies can become ordered to give you an interesting lattice, which is a repeat of something that looks like this. And this thing, this is my student Han Wu here, he called the clover lattice, the unit. And it turns out the yellow and the red sites are actually different iron sites. This is an example of a bipartite crystal lattice, which means that nearest neighbor hopping is always between two different sublattices. And theoretically, it's also been known that if you have a bipartite lattice where the number of sites belonging to the different sublattices are different, in this case there are 2 versus 3, then you're guaranteed to have zero modes, which are these topological flat bands. And then, of course, if you include SOC, you would get this become gap, and this becomes gains the Chern number here. So to make a long story short, we actually saw this in this iron 5 germanium tellurium, which is a van der Waals ferromagnet, and it was actually known already that you can actually put the states either in this disordered phase or the ordered phase. And what we found is that we can directly see the different consequences on the electronic structure. In this case, the overall crystal symmetry is actually, global symmetry is preserved. We end up with Dirac points at the K point. And in this case, there is some symmetries that are broken that lifts Dirac points. And then instead we see these flat bands in the momentum space, which we understand to be associated with the switching on and off of this destructive interference. So this paper has the details of how we actually do this. But the interesting thing also is that we have also demonstrated in this paper, you can actually switch between one state to the other by a very simple thermal method. So you just gently melt the sample, not melt the sample, but raise the temperature above some certain temperature. And then if you either slowly cool it down or quench it, if the sample prefers to sit in one or the other. And we have demonstrated you can switch from one to the other in the situation. So therefore, this is actually quite an interesting material that we're working with. That's it. So I've showed you some examples of our explorations in terms of looking for topological flat bands in bulk quantum materials. I think the goal is that we hope to be able to identify more material platforms where experimental probes that can access these bulk samples can actually can actually be used to look at how these flat bands play a role in emergent phases in these materials. Okay, that's it. I just want to thank all of the collaborators. There are many. I've flashed by many along the way, and also my group and also the beamlines that we utilize in North America for carrying out many of these measurements. Thank you very much. A-type AFM. So it's in plane, it's ferro, and then it's antiferrally stacked.
So I'm a little confused why the band's still split.
Yeah.
The moment is zero, then why did they still split?
So if it's truly Neo type AFM, then they wouldn't split. So here, oh, let me scroll past. Where is my?
I guess another way to
Yeah.
ask it is will this happen on all A-type antiferromagnets?
So here, I guess because largely the in-plane Kagome layers are preserved, so we can sort of think about what happens within each layer. And within that layer is ferromagnetic. So basically, if you calculate the spin majority states, this could be like spin down is spin majority, spin up is the minority. But if you go to the other layer, it gets swapped. But within each layer, it seems like, at least from DFT, this picture is correct, that you can, within each layer, for projecting the spin minority, spin majority states, it looks like a spin splitting. But the flavor of spin up versus spin down would change. But overall, if you do spin polarized arpads on this, you would not see spin polarization on the bands, I guess, yeah. Yeah. It's good to see you.
Is there any interplay between the CDW and the
Yeah, that's a good question. I think, yeah, so the magnetic moment below the CW order is enhanced, seen by neutron. So at least it seems like
what's the name?
Neo temperature is 410 Kelvin. CW is around 100K. And from neutron, you can see an enhancement of the moment below the CW order. If the precise
So the CW is 2 by 2.
in plane, there's an out plane component as well. Yeah.
And that's with respect to the antiferromagnetic itself?
No, just the normal state. Yeah. So you can see the. Oh, yeah. So here. This is I didn't label this. This is the L direction. This is H direction. So this So this is the magnetic Bragg peak, and then this is the CW which appears, which is 2 by 2 in the in-plane direction. Yeah.
So you get this number of ferromagnetism in the flat band, but you can also have some superconducting instability there. And so you didn't talk too much about it, but in this phase diagram or circle, you have superconductivity. So is this coming from density of space from the flat band? How do you is there an intuitive way to understand if you're going to get ferromagnetism or superconductivity?
I think as an experimentalist, I don't think there's a good answer to this. So for the case that's shown here in the circles, this is the superconductor is the 135, and I for this one the flat band is not at the Fermi level. This is the one where the Van 't Hoff singularity is the Fermi level. So what is the order of superconductivity? I think that's still open. There is this new compound, which is, I think Feng showed a poster slam, this chromium-based Kagome system that has some sort of order at ambient pressure, and then with hydrostatic pressure, that order gets suppressed, and eventually you get superconductivity. In the phase diagram, that looks really like all the other unconventional superconductors. That one may be very interesting, but I think that's to be seen. Yeah.